The Broken Umbilical Cord, AI, Memory, and the Lost Genealogy of Ideas. Summary statement. Artificial intelligence has dramatically increased our capacity to generate, branch, and connect ideas, but our ability to preserve the pathways between those ideas has not kept pace. A valuable insight can survive perfectly intact inside an AI archive while becoming functionally lost because the conversation that produced it began somewhere entirely different. The knowledge survives. The conversation survives. The archive survives. The lineage disappears. As human reasoning becomes distributed between internal memory and external systems, conversations, models, files, and platforms, the problem shifts from information storage to intellectual lineage. It is no longer enough to preserve what was said. We need to preserve where an idea came from, what prompted it, which tangents mattered, how unrelated concepts became connected, and how one line of reasoning evolved into another. Losing that genealogy does more than make an idea difficult to find. It weakens our ability to reconstruct its assumptions, cross-examine its reasoning, recover abandoned branches, and continue its development. The problem is not simply forgetting an idea. It is severing the path that gives the idea its context, its provenance, and its future potential. Part 1 of 3. The paradox: nothing was lost, yet the idea was missing. There is a peculiar new form of forgetting emerging in the age of generative artificial intelligence. Nothing actually disappears. The conversation still exists. The words are still sitting on a server somewhere. The questions, responses, timestamps, and conclusions may all remain perfectly intact. Search histories survive. Chat histories survive. Files survive. Screenshots survive. And yet an idea can become effectively lost. That distinction matters. Traditional information loss occurs when the information itself disappears. A notebook is destroyed. A hard drive fails. A document is deleted. The record no longer exists. What is happening with AI-assisted thought is different. The record survives, but the pathway to the record disappears. That is what makes the problem so deceptive. We have spent decades improving our ability to store information. Storage has become extraordinarily cheap. Cloud systems can preserve enormous quantities of text indefinitely. AI platforms can retain hundreds or thousands of conversations. Search engines can index billions of documents. But preservation is not the same thing as retrieval. And retrieval is not the same thing as reconstruction. An idea does not necessarily arrive with a convenient label attached to it. It may emerge halfway through a conversation about something else entirely. It may begin with a financial question, pass through an argument about market structure, encounter a problem involving measurement, and suddenly produce an insight about artificial intelligence. The final idea may have almost no semantic resemblance to the question that started the conversation. That is where the umbilical cord breaks. The culprit conversation. A real example makes the problem much easier to see. The missing idea was relatively simple. Could an interaction with artificial intelligence itself be evaluated and assigned a score? Could the AI analyze the quality of a conversation, its originality, reasoning, usefulness, depth, novelty, or some combination of those qualities, and generate an AI-assigned rating? The idea was remembered. Its significance was remembered. There was even enough memory of the concept to know that it had emerged during an earlier AI conversation. What could not be remembered was where. Searching for it by subject was almost useless because the originating subject had nothing obvious to do with conversational scoring. Eventually, the culprit appeared. 4th of February 2026, Athena, USDE DPEG, /AI rating system. The title itself exposes the problem beautifully. The conversation had begun around USDE, Athena synthetic dollar, market dislocations, liquidations, and questions surrounding how exchanges and algorithms had behaved during a period of instability. That was the trunk of the conversation. But somewhere downstream, after the original subject had largely done its intellectual work, the conversation wandered. The discussion moved from evaluating financial mechanisms toward evaluating explanations, reasoning, and interactions themselves. Then came the conceptual jump. If an AI can analyze an argument, identify its strengths and weaknesses, assess creativity, and compare competing explanations, perhaps the conversation itself can become the object being evaluated. The AI would no longer merely participate in the conversation. It could score the conversation. That insight eventually developed into a much larger idea around conversational evaluation and standardized scoring. But nothing about the phrase Athena USD would naturally tell the human mind to search there for it. The idea and its storage location had become semantically detached. Recognition versus recall. Recovering the conversation exposed another important distinction. The idea was not recovered through perfect memory. It was recovered through recognition. Fragments appeared, titles appeared, dates appeared, conversation identifiers appeared. Eventually, something familiar triggered the connection. That small cognitive event reconstructed the missing pathway. This is profoundly different from asking the brain to recall the location directly. Human memory is extraordinarily associative. We remember through relationships. An image triggers a place, a phrase triggers a conversation, a smell triggers a childhood event. One argument suddenly reconnects us with another argument encountered years earlier. But those associations are irregular. They are not database keys. A person may remember an idea vividly while having almost no reliable access to the chain of circumstances that produced it. The memory retains the destination while gradually losing the route. AI makes this problem more severe because it dramatically increases the number of routes we travel. A single conversation can move through economics, technology, philosophy, psychology, and product design without ever formally announcing that it has changed subject. The human and the AI simply follow the reasoning wherever it goes. That is precisely what makes generative conversation powerful. It is also what makes it difficult to archive. How ideas actually emerge. Most information systems are built around a relatively orderly assumption. A document is about something. Therefore, give the document a title describing what it is about, put it somewhere sensible, and retrieve it later by searching for that subject. That works reasonably well for static documents. It works much less well for thought. Thought is branching. A question produces an answer. The answer exposes an assumption. The assumption produces an objection. The objection creates an analogy. The analogy connects the discussion to another field. That connection produces a new abstraction. Suddenly, the most valuable idea in the conversation is something nobody intended to discuss when the conversation began. The intellectual pathway may look something like this: question, response, objection, tangent, analogy, abstraction, new idea. The final node is not necessarily predictable from the first. Indeed, some of the most interesting ideas are valuable precisely because they were not predictable from the first. This creates a fundamental conflict between the way ideas emerge and the way digital systems catalog them. Digital archives want categories. Human thought creates trajectories. The destination is not the journey. This distinction also explains why simply extracting the final conclusion is not always sufficient. Suppose the AI-assigned scoring concept had been copied into a separate note. AI conversations should be independently evaluated and assigned standardized scores. The idea would have survived, but much of its intellectual structure would have disappeared. Why did the idea arise? What problem was it originally solving? What assumptions preceded it? What alternatives were considered? Which objections caused the idea to change? Which apparently irrelevant tangent produced the breakthrough? Those questions concern provenance, and provenance becomes increasingly important when AI is involved, because AI conversations are not merely repositories of answers. They are environments in which reasoning unfolds interactively. The conversation is not simply the container. Sometimes the conversation is part of the intellectual machinery that produced the result. Remove the machinery, preserve only the output, and something important has been lost. You still possess the destination, but you no longer possess the map. And once that distinction becomes visible, the larger problem begins to emerge. Generative AI may have solved an enormous part of the problem of producing ideas while simultaneously creating an entirely new problem, preserving the genealogy of how those ideas came into existence. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Part 2 of 3. From a storage problem to a lineage problem. For most of the digital era, the central information problem was storage. How do we preserve more data? How do we make it searchable? How do we synchronize it between devices? How do we ensure that it survives hardware failure? Those problems have largely been solved. Generative AI introduces something different because the unit being preserved is no longer simply a document. It is a developing chain of thought between a human and a machine. That chain can branch, reverse direction, incorporate new evidence, abandon earlier assumptions, and suddenly connect two subjects that appeared unrelated 20 minutes earlier. The archive can preserve every word of that process and still fail to preserve its intellectual structure. That is the paradox. We can preserve the transcript without preserving the genealogy. A conventional search system asks, what document contains these words? A lineage system would ask, where did this idea come from? Those are fundamentally different retrieval problems. The first searches information. The second reconstructs intellectual ancestry. The two memory systems. Once AI becomes part of everyday reasoning, human knowledge effectively becomes distributed across two different systems. The first is internal cognitive memory. This contains impressions, intuitions, associations, fragments, and the vague feeling that something important was discovered somewhere. It is extraordinarily flexible. It is also unreliable. The second is externalized digital memory. This contains transcripts, files, timestamps, conversation IDs, search histories, screenshots, and generated outputs. It is extraordinarily precise. It is also largely incapable of understanding why one piece of information matters to another unless that relationship has somehow been encoded. The strange situation is therefore this. The human remembers the relationship but forgets the location. The machine remembers the location but may not know the relationship. Each system possesses half of what is required. The broken umbilical cord exists between them. The human mind may remember, there was something important about rating AI conversations. The archive knows. Conversation 2018-8507-6795-6742-162 exists. But neither fact alone is enough. The recovery only occurs when those two fragments are reconnected. That is why metadata can suddenly become enormously valuable. A date, a conversation identifier, a title, a public share link, a phrase buried inside a transcript. None necessarily contains the idea itself. They function as coordinates back into the intellectual landscape. Why search is not enough? This also exposes the limits of keyword search. Keyword search assumes that we remember enough about the thing we are looking for to describe it. But sometimes we do not. Sometimes what survives is merely the shape of the thought. You remember that an important connection was made. You remember approximately when. You remember perhaps one unusual phrase. You remember that the conversation somehow wandered into another subject. But you cannot reconstruct the correct search query because the association you need exists only partially in memory. The search box then presents a cruel little problem. Tell me what you are looking for, and I will find it. But if you could accurately describe what you were looking for, much of the retrieval problem would already be solved. This becomes especially severe when the desired idea was produced through a tangent. Imagine searching an archive for AI conversational scoring and receiving nothing useful because the relevant discussion is filed under Athena USD DPEG. The database is not malfunctioning, the title is not necessarily wrong, the human memory is not necessarily malfunctioning either. The problem is architectural. The conversation contains multiple conceptual identities. A conventional archive has assigned it one. The importance of tangents. This leads to a counterintuitive conclusion. Tangents are not necessarily noise. In generative conversation, tangents can be productive search paths through conceptual space. A discussion begins at point A. Neither participant knows that point G exists, but A produces B. B suggests C. C collides with an unrelated idea, producing D. D exposes a general principle. That principle produces G. If we preserve only A and G, we retain the beginning and the breakthrough, but we lose the mechanism that connected them. And that mechanism may itself contain reusable knowledge. The tangent explains how the conceptual jump became possible. This is particularly important for creative and analytical work because breakthroughs frequently occur at boundaries between domains. Finance collides with psychology. Physics collides with economics. AI collides with information architecture. A problem with an exchange algorithm unexpectedly produces a question about evaluating conversations. These transitions are difficult to predict precisely because they are emergent. A sufficiently intelligent archival system, therefore, should not merely tolerate tangents. It should detect them. It should recognize a new conceptual branch began here, and perhaps this branch later became important. The contextual cloud. There is another complication. Ideas rarely emerge from a single prompt response pair. They emerge from what might be called a contextual cloud. The cloud includes the original question, previous assumptions, corrections, analogies, disagreements, examples, failed formulations, and seemingly irrelevant observations surrounding the final insight. Some parts of that cloud are essential, others are disposable. The difficulty is that we often cannot know which is which until after the insight has emerged. This creates a temporal problem. At the beginning of a conversation, everything looks provisional. At the end, certain earlier moments suddenly become important because we now understand what they led to. Meaning can therefore travel backwards through a conversation. A casual remark made 30 exchanges earlier acquires significance only because of what happened later. That is extraordinarily difficult for conventional filing systems to represent. A folder is static, a file name is static, a chronological history is mostly static. But the meaning of a conversation can change as the conversation develops. The intellectual structure is dynamic. Cross-examination makes the problem larger. The problem becomes even more complicated when reasoning is distributed across multiple AI systems. One conversation begins in one model. Its conclusions are transferred to another. The second model challenges the assumptions, identifies weaknesses, or introduces another conceptual branch. The revised argument then returns to the first system. A document is created, a screenshot is saved. Another conversation begins 3 weeks later. An old idea is revived. The genealogy now crosses platforms. There is no longer a single conversation containing the complete intellectual history. The idea has become distributed. This is the natural consequence of using different AI systems for different cognitive functions. One may be better at exploration. Another may be better at criticism. Another may be better at retrieval. The human effectively becomes the intermediary carrying intellectual state between machines. Copy, paste, summarize, cross-examine, return, revise, archive, repeat. It works, but it creates friction, and that friction reveals something important. The user is manually performing a function that the information architecture itself does not yet adequately provide. The human is maintaining the genealogy. Friction as an accidental teacher. There is an irony here. The deficiencies of these systems can themselves become educational. When contextual memory is limited, the user learns to create summaries. When conversations cannot communicate with one another, the user learns to construct contextual clouds. When different models produce different conclusions, the user learns cross-examination. When chronological histories become unreliable, the user begins adding dates. When titles fail, metadata becomes valuable. When search fails, the user begins preserving links. When one model cannot retrieve something another model can, the user learns that apparently similar AI interfaces may possess radically different capabilities. Each irritation produces a workaround. Each workaround reveals another layer of information architecture. The friction becomes a teacher. But there is a limit to how much friction should be romanticized. A workaround is evidence of ingenuity. It is also evidence of a missing capability. The fact that a determined user can manually reconstruct an intellectual genealogy does not mean the underlying system is adequate. Quite the opposite. It demonstrates what the system should eventually learn to do automatically. What should actually be preserved? The answer cannot simply be, save everything. We already save enormous quantities of information. That is how we arrived at the problem. The challenge is not preserving more data. It is preserving relationships between data. A future AI memory architecture would therefore need to capture several different things simultaneously: the conversation itself, the concepts contained within it, the moments where the subject changes, the ideas that emerge, the ancestry of those ideas, the later conversations in which those ideas reappear, and the relationships between apparently unrelated discussions. The archive begins to resemble something closer to a graph than a filing cabinet. A conversation is one node, an idea is another, a later refinement is another, a contradiction is another. A cross-examination performed by another AI becomes another. The important information lies not merely inside the nodes, it lies in the edges between them. And that changes the nature of the problem completely. We are no longer designing better chat history. We are beginning to describe something much more ambitious, an external memory system capable of preserving the evolving genealogy of human thought. This content is brought to you by Bobby Giggs. Promote your brand here and reach a wide audience across platforms like YouTube, Instagram, and Facebook. Follow the links in the description to get started. Part 3 of 3, From Chat History to a Genealogy of Thought. Once the problem is framed this way, the inadequacy of the current model becomes obvious. A chat history is essentially a ledger. Conversation A happened on Monday. Conversation B happened on Tuesday. Conversation C happened on Wednesday. The chronology is preserved, but chronology is not meaning. Human thought does not organize itself exclusively by date. It organizes itself through association, recurrence, contradiction, refinement, and synthesis. An idea encountered in February may suddenly connect with something discovered in July. A concept developed in economics may become useful in artificial intelligence. An observation about physics may later become the foundation of an argument about markets. The important relationship may cross months, applications, and disciplines. What matters is not simply, what did I discuss on this date? It is, what did this discussion eventually become connected to? That is a different architecture. The conversation as a knowledge graph. The obvious conceptual model is a graph. Instead of treating every conversation as an isolated container, the system could treat conversations, ideas, and conclusions as interconnected objects. One conversation might contain several major conceptual nodes. Those nodes could connect to earlier conversations. They could branch into later conversations. They could be challenged by another model. They could eventually become an article, thesis, application, or product. The archive would therefore preserve not simply the existence of an idea, but its developmental history. For example, USD-DPEG leads to exchange algorithms and liquidation mechanisms, which leads to evaluation of system behavior, which leads to evaluation of AI responses, which leads to AI-assigned conversational scores, which leads to standardized conversational evaluation, which could ultimately lead to a marketplace for high-quality human AI and AI-AI conversations. Suddenly, the strange path makes sense. Viewed only from the first node and the last node, the relationship looks absurd. Viewed as a sequence, it becomes intelligible. That sequence is the genealogy, and once preserved, it becomes reusable. Provenance is part of the knowledge. This suggests a deeper principle. The origin of an idea is itself information. We often treat provenance as administrative metadata. Who wrote this? When? Where was it published? Which file contains it? Those questions remain useful, but AI-assisted reasoning introduces another kind of provenance. How did we get here? That question captures intellectual causality. It records which observation produced which inference. Which objection forced a revision? Which tangent created a breakthrough? Which external source changed the argument? Which AI challenged it? Which human judgment rejected the challenge? Which version eventually survived? This matters because conclusions detached from their provenance become difficult to evaluate. A statement may sound persuasive, while depending on an assumption that was introduced 50 exchanges earlier. A model may produce an elegant conclusion after misunderstanding the premise. A later conversation may refine the idea so substantially that the original version should no longer be treated as authoritative. Without genealogy, all of those outputs can sit beside one another in an archive as apparently equivalent pieces of text. With genealogy, they become stages of development. That is much closer to how knowledge actually works. The importance of failed branches. There is another consequence. A useful genealogy should not preserve only successful conclusions. It should preserve important failures. Suppose an argument develops through 5 possible explanations. 4 are rejected. 1 survives. A conventional summary will probably retain only the survivor. But the rejected explanations have informational value. They tell us what has already been considered. They prevent future reasoning from unnecessarily repeating the same dead ends. They show why the surviving explanation became preferable. And if new evidence appears later, one of those discarded branches may suddenly become relevant again. This is how scientific notebooks work. It is how engineering development works. It is how serious intellectual work works. Failure is not always waste. Sometimes failure is mapped territory. An AI memory system that compresses every conversation into a neat final answer risks systematically destroying precisely this kind of information. The cleanest summary is not necessarily the richest memory. Memory should be layered. The solution, therefore, cannot be infinite verbatim recall alone. That produces another version of the same problem. Perfect preservation accompanied by impossible navigation. What is needed is layered memory. At one level sits the original transcript. Above that sits a structural map of the conversation. Above that sit the principal ideas and conclusions. Above those sit relationships to other conversations and concepts. The user should be able to move in either direction. Start with the idea and descend into its origin. Start with the conversation and discover what eventually grew out of it. Start with a conclusion and inspect the objections that shaped it. Start with a current problem and discover forgotten conversations that contain structurally similar reasoning. The system would no longer merely retrieve text, it would reconstruct context. AI as the librarian of its own conversations. This is where artificial intelligence becomes uniquely suited to solving a problem that artificial intelligence itself has helped create. Traditional software struggles with conceptual relationships because those relationships are rarely explicit. AI can infer them. A sufficiently capable system can recognize that two conversations separated by months are discussing the same underlying principle, even when they use completely different vocabulary. It can recognize that an argument about housing and an argument about monetary policy share a common structural assumption. It can recognize that a conversation about a stablecoin unexpectedly generated a product design concept about conversational scoring. It can identify conceptual descendants. It can identify contradictions. It can identify abandoned branches. It can identify recurring questions. And critically, it can ask, have we encountered something like this before? That changes memory from passive storage into active intellectual infrastructure. The archive begins participating in reasoning. From retrieval to rediscovery. The distinction is important. Retrieval means find the thing I asked for. Rediscovery means find the thing I have forgotten how to ask for. The second capability may ultimately be far more valuable. A human being cannot search for a connection they no longer consciously remember, but an AI examining the genealogy of previous conversations could surface it. You begin discussing conversational marketplaces. The system recognizes an ancestral branch from a months-old discussion about evaluating AI interactions. It surfaces the connection, not because the same keywords appeared, because the underlying conceptual structure matches. The broken umbilical cord is repaired automatically. The externalization of associative memory. At that point, something significant has happened. Human beings have always externalized memory. Writing externalized facts. Libraries externalized accumulated knowledge. Search engines externalized retrieval. Cloud computing externalized storage. Generative AI externalizes portions of reasoning. The next step may be the externalization of associative memory itself. Not merely remembering information, but remembering relationships between ideas. Not merely preserving conclusions, but preserving intellectual ancestry. Not merely recording where we went, but reconstructing how we traveled there. This would not replace human memory. It would compensate for one of its fundamental limitations. The mind is extraordinarily good at making connections. It is considerably worse at maintaining a complete index of every connection it has ever made. AI could become that missing index. The broken umbilical cord. The February conversation demonstrates the problem in miniature. Nothing had been deleted. Nothing had been destroyed. The conversation remained available. The idea remained valuable. The user even remembered that the idea existed. And yet, reconnecting the idea to its origin became an unexpectedly difficult forensic exercise. The failure was not storage. It was not intelligence. It was not even memory in the conventional sense. It was lineage. The connection between an idea and the journey that produced it had been severed. That is the broken umbilical cord. And as generative AI becomes embedded more deeply in research, writing, investing, engineering, science, creativity, and ordinary thought, this problem will become larger. We are generating intellectual material faster than any previous generation. We are branching across subjects faster. We are moving between machines faster. We are producing more conversations, more hypotheses, more revisions, and more conceptual fragments than human memory was ever designed to catalog. Saving all of it will not solve the problem. Searching all of it will not solve the problem. Even remembering all of the conclusions would not solve the problem. Because knowledge is not merely a collection of destinations, it is also the network of paths connecting them. The next great challenge in AI memory may therefore have surprisingly little to do with increasing storage capacity. It may be about preserving intellectual continuity. The knowledge survives. The conversation survives. The archive survives. But unless we preserve the genealogy of thought, the route by which one idea became another can disappear. And when that happens, we have not lost the answer. We have lost the path that made the answer possible.